Hi everyone, today we're going to talk about polarity. An atom has a certain property called electronegativity. Electronegativity is an atom's ability or tendency to pull electrons shared in a bond toward itself. So if I have an atom here and an atom here, and this one's more electronegative and they're sharing electrons in a bond, then this one's going to be more greedy for the electrons. So it's going to pull the electrons toward itself and become more negatively charged because electrons are negative. So if this one's more electronegative, then the electrons get pulled this way. That creates a difference in charge, and we call those partial charges. So this one's more partially negative, this one's more partially negative. The other one is more partially positive as a result. This creates something called a dipole or dipole moment. All right, those electronegativity values are a periodic trend. If you look at the values here, these are the Pauling electronegativity values. You can see that the most electronegative element, or the one with the highest value, is fluorine. And the lower end is down here on the opposite corner of the periodic table. So what that tells us is if we go toward left to right, we end up with higher values. So they're generally increasing. And I abbreviate electronegativity EN. And then also if you move up, you also increase the electronegativity value. So remember that the polarity, or how polar the bond is, depends on the difference of the electronegativity. So picture two twins, they have the same properties. So there's no preference one way or the other. They share the bond equally. That's called a nonpolar bond. And remember, a polar bond is the uneven sharing or distribution of the electrons. So let's look at those differences. If you look at these bonds as examples, which of these would be the least polar, where you have equal sharing for both atoms? It would be hydrogen. All right, and so go ahead and try to figure out what these are. Okay, so now we've ordered our bonds from least polar to most polar based on their electronegativity difference. What that means is the electronegativity value of hydrogen is 2.1. So 2.1 minus 2.1 is 0. Carbon 2.5 to 2.1 for hydrogen, so it's a difference of 0.4. Generally, an electronegativity difference of less than 0.5 is going to be what we consider nonpolar. Even though there's a little bit of difference between here, carbon and hydrogen, it's still generally considered not very polar. Okay? Up here is something I would call very polar because the difference is quite high. Generally, something that's like 1.5 or 1.8 and higher is considered pretty polar. We visualize the dipole as usually either an arrow with a little crossbar on it, like this, or we show partial positive and partial negative charges. The arrow points toward the negative, more electronegative element, and this crossbar looks like a positive sign, so that reminds me that's the partial positive end. So using either of those symbols, if we assume that we have a molecule like atom A and atom X, and they're bonded together, let's say X is more electronegative than A. Then there's going to be a dipole this way, and this way. Now, what shape is this? If you look, it's got a steric number of 3. There's no lone pair. So this is trigonoplanar. So that's flat. And these lines and dashes and wedges are basically telling you that there's one that's in the plane, that's this one, and there's one sticking back behind you, that's this one, and one sticking forward toward you, that's this one that's wedged. So this notation is trying to show you that they're pointed in all directions in 3D. That means that the dipoles are actually canceling each other. This one's going to cancel this direction versus that direction. You have the forward direction versus the back direction, and they're all distributed by 120 degrees equally all the way around. So this is an example of a highly symmetric molecule. So we're going to say the dipoles cancel, and this is nonpolar. So molecules with this shape that have the same atoms attached, and so they're going to have the same dipoles going around, and they're all going to cancel. The same type of thing happens here. So you've got the dipoles pointing in all directions equally. All the bond angles here are 109.5. So this is also a case where the dipoles will cancel. What we see here are, what shapes are these, by the way? Let's review. Here, this is based on a steric number of 4 tetrahedral geometry, but the shape is pyramidal. So here we have one of the dipoles is going to be different from the others because of this lone pair. So instead of being tetrahedral shape, it's now pyramidal shape. So there will be an uneven distribution, meaning this side of the molecule down here will be more negatively charged than the top part, potentially. Or maybe the top part is more negatively charged, since there's a lone pair there. So anyway, it just means there's a difference in the way that charge is distributed. If you look over here, same idea. So you've got these lone pairs here, and then you have these atoms here. So you have some difference in a dipole. You have a dipole moment that does not cancel. So this is also considered polar. So polarity also determines physical properties such as boiling point, melting point, and water solubility. So let's review that and what role intermolecular forces play in that. So let's review intermolecular forces. I want to contrast this with intramolecular forces. Intramolecular forces are the attractions within molecules. Intra means within. So if I have a molecule, the intramolecular forces are within this molecule. So it is the actual bonds, like the covalent bonds. In contrast, intermolecular forces are the attractions between molecules. So in thinking about that, we need more than one molecule then. So here's another molecule, and then they're going to attract each other. And we call that the intermolecular force. So one analogy I have, which I learned from my colleague, Jack Surendranath, was to tell the difference between these two types of forces. You have a person, like draw a stick figure. So here's a person, and here's another person, and they represent molecules. So this one's one molecule, and this one's the other. The intramolecular force is within the molecule. So it would be like this person's arm connected to his body or something like that, right? So these are the forces that connect us to be a whole person. The intermolecular force then would be, if they held hands together, that would be the intermolecular force. So when you give these two people energy, they're going to break apart where? Hopefully they break apart here, okay? Otherwise it'd be pretty gruesome. So that is the intermolecular force, whereas these are like the covalent bonds. The name of the IMF, or the type of IMF that's involved, is going to be based on the polarity of these molecules. And remember, like dissolves like. Okay, so if those two molecules are considered nonpolar, what tells me that this is nonpolar? I'm looking for the type of bonds that are involved here. Remember, the more polar bonds, the more polar the molecule, generally speaking. So nonpolar will tend to have molecules that have CC bonds, HH bonds, or CH bonds. Remember, these are not very polar. It could also mean that the dipoles cancel out. That also makes it nonpolar. The type of IMF between nonpolar molecules is called the London dispersion force, or just dispersion forces. Polar molecules have a dipole. So generally, since we are carbon-centric in organic chemistry, we're going to talk about carbon-nitrogen, carbon-oxygen, and carbon-halogen bonds. And these types are called dipole-dipole. And that's because this molecule, if it's polar, has a dipole. This molecule would have a dipole, and then the force between them is called dipole-dipole. There's an extreme case of when you have a very polar molecule. You're going to have an extreme difference in electronegativity. So these types of bonds here, nitrogen with hydrogen, oxygen with hydrogen, and fluorine with hydrogen, because those electronegativities are so different from each other, they're going to be even more polar bonds than usual. So in that case, what we see are IMFs called hydrogen bonds. Now, these are not hydrogen-hydrogen bonds. They are called hydrogen bonds because electronegativity difference is greater when you have something with a small electronegativity, and hydrogen has a small electronegativity compared to the other types of atoms we see, like nitrogen, oxygen, and fluorine. Okay, so I would think of these as two separate molecules, and then there's some kind of force of attraction between them. In this case, these are nonpolar, because not only are they carbon-hydrogen bonds, which are not very polar, but their dipoles cancel out because they're in all directions. So nonpolar, this will be dispersion forces. In this case, we have two different molecules, in this case, we have water, and water has OH bonds, so they're extremely polar. To draw the intermolecular force between them, I would determine where's the electronegativity highest, oxygen or hydrogen. So it's higher with oxygen. So I'm going to draw a dipole like that, and I'm going to draw a dipole like this. And the intermolecular force is specific, between the positive and the negative. So I want to look for the negative region, hydrogen bonding to the positive region of a different molecule. Okay. So it's from the lone pair or the negative charge on this oxygen with this positive charge to the hydrogen. So that is what we call the hydrogen bond. And remember, it's not a covalent bond, it's an intermolecular force. Our last example here are carbon monoxide molecules, and I've drawn them with their formal charge. Okay, this is the way we usually think of them. And in this case, you see the negative and the positive already. So there's going to be intermolecular force of attraction this way. And what would they be called? Well, CO is polar, but not very polar, so we would call these dipole-dipole. And that's because we have a dipole going this way and a dipole going that way, and these two dipoles are attracted to each other. So back to our activity, what I would like you to do here is play the role of a scientist. You have some data on the next page of different groups of molecules listed by their functional group, alkanes, alcohols, and ethers, and these are different molecules but with the same functional group. You'll see that their weights and their dipole moments and their boiling point and water solubility are provided here. I want you to go through these questions, number 3, and the rest of these here. And I'd like you to think about how to use the data to draw some conclusions about polarity and the strength of the intermolecular forces. All right, when we look at these data and we want to answer the question, which of these functional groups seems to be the most polar, I would probably just go with the dipole at first. Okay, so dipole is 0 here for alkanes, 1.7 for the alcohols, and 1.3 for the ethers. So generally the dipole moments that are measured in debye's, they are higher for the alcohols. Within a functional group, what factors affect the boiling point? So why is propane's boiling point lower than butane's? So let's look at these two. The boiling point is much lower for propane than butane. The difference between these structures is the addition of a carbon unit. So that makes the molecular weight different. So if you remember back to general chemistry, when you have different molecular weights, due to more electrons, you have more interactions between those electrons, so you've got greater dispersion forces. So in general, that's how we think of dispersion forces. They're actually in all molecules. It's due to their electron clouds and the instantaneous dipoles that are experienced within any molecule with electrons. So the more electrons you have, the more mass you have, the more dispersion forces you have. Name the type of intermolecular forces that predominate between molecules within each functional group. So alkanes are nonpolar, so they're dispersion, because they are the C-C bonds and the CH bonds. Alcohols have the OH bonds, which make them very polar, so they undergo hydrogen bonding. And ethers have a CO bond, which is pretty polar, but they also have the C carbon-hydrogen bonds and sometimes carbon-carbon bonds. So those parts can make them nonpolar. So I would say dispersion forces apply for all of them, but especially for alkanes, and for ethers, dipole-dipole and dispersion forces. Based on your answer above, which functional group is most water-soluble? So if you think about water, water's very polar, and alcohols, OHs, are very polar, so they have a compatible intermolecular force, which is hydrogen bonding. So that's where we get the term like dissolves like. Nonpolar with nonpolar, dispersion forces, polar with polar, dipole-dipole. Hydrogen bonding is for very polar with each other. Now there is an exception. As you increase, you've got this molecule which is not so high in solubility, but still pretty high compared to the other groups. But you can notice a trend that the water solubility decreases as the alcohol chain gets larger. In the next question, butanol has a larger boiling point than propanol. Why is that? So that is the idea of the longer carbon chain. The carbons that grow make the molecule more nonpolar. So even though you have this polar part, the OH group, the more nonpolar this chain becomes, the more nonpolar overall the molecule will become. So it can hydrogen bond at the polar head, but as the tail gets longer, it's going to be harder to form those hydrogen bonds with water. Tert-butanol is this molecule, and butanol is this molecule, and they have very different boiling points. This one is much higher at 118. This one, same number of carbons and hydrogens and oxygens. So it's an isomer. It's got a lower boiling point. So what does that tell you about the strength of intermolecular forces? I put that the branching appears to make the intermolecular forces weaker. Now that is due to surface area. If you have butanol, which is long chains, they're going to have more surface area to interact. So their intermolecular forces are going to be stronger, or a greater frequency of intermolecular forces. Whereas you have tert-butanol, which is branched and sort of circular shape, maybe like a glob. So these guys have just certain areas where they can interact, as opposed to the long chain ones. So the more branching you have in general, the lower the boiling point, because the weaker the IMFs due to a lower surface area. So I will add that right now. Also note that you must compare molecules with the same molecular weight or similar molecular weight in order to see the effect of things like branching, because remember, molecular weight also affects the strength of the intermolecular forces. In the next question, we have cyclobutanol, which is an isomer of butanol as well. They have similar, I think they're different by a little bit, maybe a couple of atomic mass units only, but still enough to compare them. So here, this is a much higher intermolecular, this is a much higher boiling point. And so that implies that this ring structure, as opposed to a linear structure, actually increases the strength of the intermolecular forces, which might be opposite of what we just said. If a ring structure looks like it's got a lower surface area, how come it can have a stronger intermolecular force? The reason behind that is, with the rigidity of a ring, you have the ability of stacking to occur. And when stacking occurs, it's like a pile of plates. They're really good at stacking on top of each other, so that increases the strength of their intermolecular forces. All right, with the next one, ethanol and propanol are more water soluble than butanol because the smaller the carbon chain, the smaller the nonpolar part of the molecule. So the overall polarity of the molecule is higher. Finally, our last question, butanol, here it is drawn out, and water drawn out. The OH groups are very polar, so that is where they will hydrogen bond. I would start with the dipoles and then figuring out who's attracted to who. So we've got our oxygen and our hydrogen. They would be attracted to each other. So there's one hydrogen bond. And then you could draw another hydrogen bond this way to another water molecule if you wanted to. All right, there you go.